Welcome to the course on Introduction to Electrical Engineering. We will have a lecture 30 today on transformer part 2. Starting from outline of presentation, we will like to introduce, of course, we will like to go to phasor diagram of ideal transformer at no load. Then we will like to talk about useful and leakage flux in the transformer. Then we will talk about equivalent circuit. Then we will go to approximation of this equivalent circuit and followed by phasor diagram of real transformer on load. Then we would like to talk different parts of transformer, followed by exercise and numerical problem with references like. Coming to the introduction part of today lecture, I mean this is something what we have a transformer in different industrial application. This is the transformer photograph of arc furnaces, transformer used for steel furnaces, then the transformer for rectifiers, I mean along with the rectifier in the aluminum electrolysis process. I mean there we normally in such a process we use very high current and very low voltage to form the normal supply voltage, and the rating is also substantial. So, what we have to do, we have to increase the current rating and reduce the voltage rating, and of course, we have to provide even a isolation also. Then the typical application is of your converter transformer for variable frequency type in application like pumping, mining for medium power applications. Then of course, the booster transformer in traction, typically locomotive and trains and applications. Then of course, transformers in mobile chargers as well as electronics power supply, which are high frequency transformer for impedance matching in outdoor and radio frequency devices, especially loudspeaker, and transformers in your electric vehicle for the charging system, I mean electric vehicle wireless charger. Then of course, the electric wireless charging, I mean is a part is with the resonant circuit. Then of course, typically the kind of along with some time we require even the inductors, reactors in the power grid, which are similar construction as the transformer like. Now, coming to phasor diagrams of the ideal transformer on load. So, these are typically you can call it the circuit of your ideal transformer. We have a primary voltage with primary current and secondary voltage secondary current with turns respectively, as well as the load connected to the secondary. The ideal transformer has only turns ratio as shown here. The winding resistance, leakage flux, reactances and the losses are ideally 0, and the input and output voltage and current relationship are V 2 by V 1 equal to I 1 upon I 2 equal to N 2 upon N 1, and that is maybe we normally represent by small n this turns ratio. So, we here have a like a phasor diagram of ideal. So, we consider V 1 equal to E 1 and V 2 equal to E 2, and if transformer of primary secondary are same, typically taking example of like isolation transformer, then E 1 equal to E 2, and we can say I 2 lags by V 2 by an angle phi 2, that is the load power factor angle of the load, and this is normally we consider lagging power factor load is considered here with the cos phi 2, because most of the loads are normally lagging power factor in practice. So, where the I 2 dash is the component of primary current neutralized by demagnetizing effect of secondary current, and I 2 dash equal to opposite of I 2, and total current drawn from the supply will be then I 1 equal to I 2 dash plus I 0, that is I 0 is a no load current, and primary power factor is now phi 1, which is corresponding to cos phi 1, which is where the angle phi 1 is the angle between the V 1 and I 1, as you can see in the phasor diagram. So, we have I 0, that is at very large angle, because the power factor at no load is normally typically very low, 0.1 or 0.2. So, this angle will be large, and this is I 2 with respect to V 2, because secondary load is connected and power factor of the load is cos phi 2. Then we revert it on the other side according to turns ratio. If it is a unitary turns ratio, same value goes on, and then we have a phasor sum of I 0 and I 2 to derive the I 1, and we have an angle now of this I 1 with respect to the V 1, that is we call it now supply power factor, that is cos phi 1. So, these are typically the phasor diagrams of loaded transformer with ideal transformer, where we are neglecting of course, the resistances of winding as well as the leakage reactances of the winding like. So, now coming to discuss about useful and leakage flux in the transformer. So, we have a leakage flux, the flux linking with only one winding flows through the air path between the windings. So, we can call it the reluctance of air is around 1000 times that of core material. So, leakage flux typically will be much less than the mutual flux, and it is categorized as primary leakage flux caused by primary MMF and induces voltage in the secondary winding, and secondary leakage flux caused by MF N2 its MF N2 I2 and induced voltage in secondary winding. So, these are typical example. You can say for ideal transformer there is no leakage flux and you have primary winding and secondary winding with the load connected on secondary winding and current drawn from supply. And you can see now what is how the leakage flows. The main flux flows here, the leakage flux of the secondary flows to local path, and even for primary winding also you have a leakage flux. So, this is we call it in practice you have some leakage flux, may be quite small, but there is some leakage flux on which is not linking the another winding of on this magnetic structure like. So, leakage flux proportional to primary and secondary current, and of course, useful and mutual flux is constant at all load, and effect of primary and secondary leakage flux is in a practical transformer can be considered equivalent to an ideal transformer with additional inductive reactances connected in series with the two winding, and total flux linked by each winding may be divided into two components. One is a mutual component that is common to both winding, that is phi m, and another is leakage flux component linked only with the particular winding either primary or secondary. If it is with the primary, it is called phi 1. So, you can say leakage flux with the your winding 1 is phi L 1 and leakage flux with the secondary winding is your phi L 2. L represents the leakage. So, you can call it total flux in the primary will be phi 1, phi L 1 plus phi m, and total leakage flux in secondary will be phi 2, that is phi L 2 plus phi m. And you can clearly see how in this diagram that what is like a this is the main magnetic main flux, and this is the flux for the leakage of typically of the secondary, and this is of leakage flux of the primary. I mean of course, we define the primary which is connected to the source, and secondary we define which is normally connected to the load. So, this gives you a clear idea how it is the leakage flux is there in the transformer like. So, coming to now if typically the fringing, so magnetic fringing. So, when the magnetic field line pass through the air, they tend to be budge out, and this effect known as magnetic fringing, as you can say how it is a budging out when it is flowing through the air, or it is going to be here it is a leakage, here it is a fringing. So, this effect is known as magnetic fringing, and due to magnetic fringing the effective area of the air gap is increased, and thus the magnetic flux density is decreased in the air gap. So, the longer the air gap, the higher is the fringing and vice versa. Now, coming to the effect of primary and secondary leakage fluxes in a practical transformer can be modeled as an ideal transformer with additional inductive reactance X 1 and X 2 in series with the two winding. So, you have a like ideal transformer, you have a primary and secondary, and you have a typically transformer with leakage reactances. So, you have X 1 is the leakage for primary and X 2 is the leakage of the secondary. I mean how it is as a series reactances are really considered in the transformer along with the ideal transformer. Then we have of course, how we can reduce the this leakage flux. In many situations we have to reduce the leakage reactance as well as leakage flux. So, leakage flux can be practically eliminated by winding the primary and secondary one over the hour uniformly around the limited ferromagnetic material of uniform cross section area. It means we put the both the winding on the same structure, have the winding on one limb of primary and secondary above and below. So, that certainly reduces the your leakage flux and leakage reactances. So, principal method used in practice are making the transformer window long and narrow, and arranging the primary and secondary winding concentrically and sandwiching the primary and secondary windings, and normally using the cell type construction you can do even this kind of sandwiching construction which really can control or can reduce the your leakage flux. Now, coming to equivalent circuit of the transformer typically. So, a practical or real transformer can be treated as an ideal transformer plus additional circuit elements used for modeling the various impedance, for example, a copper losses in the primary and secondary winding, then the core losses in the ferromagnetic core which is also supplied by the supply, means core loss consists of we discuss eddy current losses as well as your hysteresis losses, and the leakage reactances of course in primary and secondary, and of course, no load magnetizing current which is responsible for providing the excitation to produce the flux like. So, now typically this is ideal transformer, and here you can see what is the practical transformer. So, you have a resistance of primary because it is bound with the copper winding, and you have a leakage reactance which we really represented. Secondary side also we have a resistance of winding, it is bound with the wire, and we have a reactance of leakage reactance of the secondary. So, this is, and we have another branch we call it shunt branch which is responsible to represent the IM no load current. So, one is the magnetizing current which is set up the flux if flowing into magnetizing reactance, that is we call it X0 or Xm or Xc, this we call it magnetizing reactance, and another is the resistance which is responsible equivalent to core loss, and the current which we call it OL, IOL, this is representing the core loss component of the transformer. They are connected in shunt because they depends on the voltage. I mean, if for a given frequency the flux depends on the voltage, if voltage is varying then the flux is also varying, and this certainly the core losses will also vary, as well as magnetizing current also will vary, as well as these parameter also changes with the this level of the flux, or you can call it when it is transformer is already wound and you have only the one frequency and voltage varying, then certainly this parameter also changes with the voltage like on. Now, so here you can just see with the how it is a equivalent circuit. So, you have a leakage inductance followed by resistance, here also secondary leakage reactance, then resistance, and then you have a magnetizing reactance as well as you have a core loss resistance. So, this we call it like a, you can call it equivalent circuit of the transformer. Normally, this of course, you can take on any of the winding side, but normally these are considered on primary side the shunt branch parameter, because even the secondary is open, still will be taking magnetizing current as well as the core losses from the supply, and that is why it is considered on the primary side. And these are the typical value in ideal transformer. The primary winding resistance as well as secondary winding resistance are 0, but practically there is some resistance here, and similarly leakage reactance of primary and secondary, that is 0 in ideal transformer, and you have here typically some finite value, and typically the magnetizing reactance which we consider infinity in case of ideal, but we have practically some value maybe in kilo ohm, and similarly core loss resistance we consider infinite, I mean in a ideal transformer, but practically there is some value of it of, and these value are much larger than your series parameter like resistance as well as leakage reactances, like they draw very less current like on. So, these are these parameters correspond to ideal transformer and different rating transformer, all these 6 parameters which we mention in the equivalent circuit means typically I mean magnetizing reactance, primary resistance, secondary resistance, core loss resistance as well as your leakage reactance of primary and secondary. These are the 6 you can call it elements in equivalent circuit of the transformer. Now, coming to an approximate equivalent circuit, what the approximation I mean is a practical ideal transformer in between, and this is a practical transformer. I mean you have a primary leakage reactance and resistance, secondary resistance and leakage reactance, and you have a shunt branch parameter, in between you have ideal transformer. So, this we call it like a this is equivalent circuit. What approximation we can take it, I mean sometimes the no load current is typically around 3 to 5% of the full load primary current. So, transformer equivalent circuit near full load includes the coil resistance, copper and leakage reactance is here. So, this is something ideal, and these are the typical with some kind of approximation. So, thus the parallel core impedance R0 and X0 can be omitted without introducing any appreciable error when considering the bear of transformer near the full load, means typically you are calculating the like a voltage regulation, they do not come into the picture like on. So, the resistances, the resistance R2 of the secondary is replaced by inserting a additional resistance R2 dash when the carrying the primary current in equivalent to that of R2 due to the secondary current. And then how we say this is when you refer really I1 square on primary side when you want to refer it. So, the loss core loss copper loss represented on primary side will be I1 square into R2 dash equal to I2 square R2, and that from where we get R2 dash square equal to R2 dash equal to R2, I2 upon I1 square equal to R2 V1 upon V2 square. So, this we are transferring from the secondary this your R2 resistance on the primary side, and this we call it is still the approximate equivalent circuit because we have neglected the shunt branch parameters here. So, now the RE is a single resistance of primary circuit of equivalent of the primary and secondary resistance. So, RE we call it R1 plus R2 dash or R1 plus R2 dash V1 upon V2 square, because we are transferring this resistance from secondary to primary side, that is why the voltage on primary side is taken, or you can call it the turns ratio taken here, and this represents the equivalent resistance. And similarly, the inductance of the coil proportional to square of the number of turns. So, the second leakage reactance also can be replaced by equivalent reactance here X2 dash equal to X2 into I2 upon I1 square equal to X2 V1 upon V2 square. So, that is also reactance, secondary reactance can be transferred to the primary winding, and this typically the Xc is the reactance of primary and secondary equivalent to of X1 X2 actual turns. So, we can say Xc equal to X1 plus X2 dash plus equal to X1 plus X2 V2 upon V2 square, that is we are transferring the from secondary to primary, and then you can call it. Now, we can add together, I mean the total impedance we can call it will be of this circuit on primary side with approximation, call it Z equal to R e square plus X e square. This we call it equivalent impedance of primary and secondary winding referred to the primary circuit, and where R e is your Z e cos phi e and X e equal to Z e sin phi e, or you can call it R e is R 1 plus R 2 square, R 2 dash square on X e equal to X 1 plus X 2 dash square like. So, this is something how we go to form steps from practical equivalent circuit to approximate equivalent circuit. So, this is the, I mean you can call it the equivalent circuit referred to the primary side, we are taking the secondary reactances on this. Then you can go to the equivalent circuit referred to the even primary, typically primary side, but in place of shunt branch parameter on this side we can take on this side, and then we can take equivalent circuit neglecting the winding resistance. So, it is a X equivalent only, or you can have it coming from here. So, R e EQ neglecting this branch, and then it can be only reactance for some calculation. Your resistance may be resistive low, I mean drop may be very small compared to the reactive interest. So, depends which kind of approximation you want to have in which circuit of this approximate equivalent circuit. So, normally this phasor diagram of this at under the loaded condition of this practical transformer, where we have a resistance and reactances here, which already we define of Z e, and that is Z e square, Z e equal to under root R e square plus X e square, where R e is Z e cos phi and X e sin phi, and here you have a like a typically the phasor diagram, we have a E 1 equal to typically V 2 dash and similarly E 2 V 2, and here we have the current, let us say I 2 going to be I 2 referring on primary side, that from which we get the I 1, and you have a typically the drop of I r plus I x, that is I z. Okay. That I z we add typically, I mean V 1. So, that we get the typically the total V 1, this we add E 1 here. So, this impedance drop plus V 1 E 1, that is virtually from this to this drop we add it. So, we get V 1, that is supply voltage. So, this is the impedance drop plus the E 1 induced EMF of the primary side. So, this you get the, and you get the phasor diagram corresponding to really here supply voltage, as well as you get the current drawn from the supply here, like I mean also with the lagging power factor, as you can say at the power factor phi 1. So, that is V 1 and I 1 is the V 1 is the applied voltage from the supply, and I 1 is the current drawn, and phi 1 is the angle between the V 1 and I 1 by this. Of course, this angle depends on the load power factor also and parameter of the transformer. So, coming to phase diagram of a transformer on load. So, here it is a, you can call it the typical phasor diagram. So, we have here V 1 equal to E 1, and we have I 0 at angle of phi 0, that is corresponding to no load current. Then we have a V 2 and I 2, that is load voltage and load current, and we reflect on the primary side. So, I 2 dash, and this we add phasor sum I 0 and I 2, that get I 1, and it is a V 1. We have a angle typically phi 1 perfect angle, and this is the we call it the phasor diagram of this ideal transformer loaded condition, which we discussed earlier too. And this is under the typically a practical transformer, which we are mentioning it here. So, we have a here E 1, which is out of E 2, and of course, taking a drop here of I 2 Z 2, that is V 2, I 2 Z 2 is here. So, from V 2 to I 2 you have a phi 2 angle, then we have a drop of your I 2 Z 2. So, you get typically E 2, and virtually this current get reflected on the other side with I 2 is, we add it here I 2 dash transfer on primary side, and then phasor sum of this is I 1, and typically here E 1, and with the E 1 we add typically I 1 Z 1, and this becomes like further adding of this both the impedance. So, you get the sum of E 1 plus this E 1 plus this impedance drop. So, you got V 1. So, this is V 1 and this is I 1 with angle phi 1. So, this is the transformer under, you can call it of a practical transformer, where you can consider for the simplicity maybe N 1 equal to N 2 and E 1 lags by power factor angle, and remaining drop are considered here practically. So, from phasor diagram you can call it V 2 equal to E 2 minus I 2 Z 2. So, power factor of the load is cos phi 2. So, where phi 2 is the phase difference between the V 2 I 2, that is load power factor angle, which really depends on, you can call it supply power factor, depends on the load power factor angle, and there is a possibility also this angle load power factor angle, if it is a leading, then there is a possibility that you can get even the power factor on the, I mean supply side also you can get the leading, even it can compensate for the your magnetizing current also like. So, Well, the power factor of the load is cos phi 2, where phi 2 is the phase angle difference between V 2 I 2 and I 2 dash is the component of primary current to neutralize the demagnetizing effect of secondary current and is drawn from opposite to I 2, and I 0 is the no load current of the transformer, I 1 is the current drawn from the supply, that is I 1 equal to I 2 dash plus I 0, where I 2 dash is the current referred of secondary current to the primary current, like primary side. So, we can call it here I 1 R 1 is a voltage drop primary resistance, I 1 X 1 is the voltage drop due to primary leakage reactance, and I 1 Z 1 is the voltage drop due to primary impedance, that is V 1 equal to E 1 plus I 1 Z 1, where phi 1 is the phase difference between the V 1 and I 1, and then cos phi 1 is the power factor of the primary side of the transformer at the supply side. So, now you can call it typically under load. So, you can recall the mutual flux taken from the as a reference phasor typically here, and E 1 is induced by primary leads by the flux by 90 degree and secondary EMF drawn in opposite direction for the convenience from E 1, and I 0 is the no load current of primary, and neglecting the coil resistance of first primary and secondary and leakage reactance of primary and secondary, you can call it V 1 equal to E 1 and V 2 equal to E 2, and load impedance of the secondary has lagging power factor phi 2. So, Z L equal to V 2 upon I 2, that is Z at the angle of phi 2, and I 2 dash is the secondary current, I 2 reflected on the primary side via the transformer turns ratio, and that is where the I 1 is I 0 plus I 2 dash, as it is shown here, is the total primary current which is lagging by V 1 by angle phi 1, that is called primary side power factor cos phi 1. And this is the practical transformer where all the components are included in this phasor diagram. I mean, the typically no load current is also included, as well as the leakage as well as resistance of the winding is considered here, from which we can induce the relation, the coil resistance R 1 R 2 and leakage reactance of X 1 X 2. So, here we can say, we cannot say that V 1 equal to E 1 and V 2 equal to E 2. We can say V 2 equal to E 2 minus I 2 Z 2, and it means that is E 2 minus I 2 R 2 minus J I 2 X 2, or E 2 equal to V 2 plus I 2 R 2 plus J I 2 X 2, and V 1 will be E 1 plus I 1 Z 1, that is E 1 plus J I R 1 plus J I 1 X 1. So, these are the typical basic equation are used normally in the calculation of the different variables in the transformer. Again, the load impedance on the secondary is taken to have a lagging power factor phi 2, and Z L equal to V 2 upon I 2, that is the impedance of the load Z L at the angle of phi 2, and primary side power factor cos phi 1, that is the load primary current lagged by the from the supply voltage V 1 by angle phi 1. So, now coming to the typically different parts of the physical practical transformer, the basic parts of the transformer are its core, primary and secondary winding. There are many different parts, different type of equipment installed in the transformer that are also considered as a part of transformer. Following are the various part of the transformer, like a laminated core, insulating material, terminals and bushing, transformer oil, tap changer, Buchholz relay, winding, tank, explosion vent, breather, radiator and fans, and oil conservator. And this is the practical transformer where all the parts are mentioned here. I mean, starting from core, then you have even a winding, conservator. I mean, typically all parts are mentioned here, and main parts of the this 3-phase transformer are laminated core, which is shown here. Then low voltage winding near to core, high voltage winding little far from the core after the low voltage winding. The 4 is the transformer tank in which this complete winding and core are put in. Then the 5 is the radiator and fans. I mean, this is the radiator fins along with the fans, and then the 6 is the low voltage bushing here, and 7 is the high voltage bushing. Then the 8 is conservators. So, you can call it what your limited core consists of. Limited core is the most important part of the transformer used to support the winding of a transformer, and it is made of laminated soft iron material to reduce the eddy current loss and hysteresis loss, eddy current loss especially. And the windings consist of several number of turns of copper conductor or maybe aluminum conductor that are bundled together and connected in series, and the main function of windings is to carry the current and produce the working magnetic field and induce the mutual EMF of the transformer action. You have a insulating material. Insulation is required between the each turn of the winding, typically between the windings, winding and core, and the current carrying part and the tank of the transformer. So, you have a different kind of insulation in a transformer, An insulating material of transformer should have a high dielectric property as well as also good mechanical strength and temperature withstand capability. So, here we have like a main tank. Main tank is the robust part of the transformer that serve mainly two purposes. It protect core and windings from the external environment and provides the housing for them, and second, it is used as a container for the transformer oil and provides the support for all other external accessories of the transformer. Now, terminal and bushings, these are connected with the ends of winding conductors, and bushings are mainly an insulator made of the porcelain and epoxy resin, and they are mounted over the tank and forms a barrier between terminals and tank. As windings are of two types, so the bushings are also of two types as name high voltage and typically low voltage. So, you can say low voltage bushing and high voltage bushing. And of course, transformer oil, the function of transformer oil is to provide the insulation between winding as well as cooling due to the its chemical properties as well as very good dielectric strength, and hydrocarbon mineral oil is used as a transformer oil as it acts as a coolant, and it is composed of aromatics, paraffin, naphthalene and olefins. Now, tap changers, the main function of tap changers is to regulate the output voltage of transformer by changing its turns ratio by 5%, and there are two types of tap changing, on load tap changer and off load tap changers. Now, Buchholz relay is the most important part of the power transformer rated more than 500 kVA, and it is gas actuated relay mounted on the pipe containing the main tank and the conservator tank, and the function of Buchholz relay is to protect the transformer from the internal fault such as short circuit fault or internal fault. The breather is a cylindrical container filled with the silica gel and directly connected with the conservator tank of the transformer, and in a breather when air passes through the silica gel, then the moisture present in the air is absorbed by the silica gel crystal, and hence a moisture free or dry air is supplied to the conservator tank. So, breather is acting as an air filter for the transformer. Now, this called explosion tank. Vent, explosion vent is a metallic pipe with a diaphragm at one end and installed on the main tank slightly above the conservator tank, and it is available on in high rated power transformer. The main function of explosion vent is to protect power transformer against the explosion during excessive pressure built up in the main tank due to several internal faults. Now, coming to radiator and fans, the cooling arrangement is required for the power transformer. The main function of cooling tubes or radiators is to transfer the heat generated by the core and windings to the environment by circulating heated oil through the cooling tubes, and of course, dry type transformers are generally natural air cooled, and in large power transformer force cooling is achieved with the help of cooling fans fitted on the radiator. Now, coming to oil conservator, the function of oil conservator tank is to provide the adequate space for expansion and contraction of a transformer oil according to the variation in the ambient temperature of the transformer oil inside the main tank, and in a cylindrical drum type structure installed on the top of the main tank of the transformer, and it is connected to the main tank through a pipe and Buchholz relay mounted on the pipe. Now, coming to the typically the theoretical problem. So, can we say question number, can DC can be applied to transformer? No, because reactances will not be in function, you will have very small resistance only on the DC. So, one is the transformer work on Faraday law of magnetic induction, for which the current in the coil must change. So, if DC is applied, current will not change and transformer will not work. Practically winding resistance is small for a DC, inductive reactance is 0 and frequency is 0. Therefore, the impedance is low, thus the winding draws more current, which may damage the winding, and there is no induced voltage because there is no rate change of the flux by exciting the transformer primary winding with the DC current. So, now question 2, what are the property of ideal transformer? The answer is there should be no losses, the winding should have 0 resistance, the leakage reactance should be 0, and the permeability of core should be so high that the negligible current is drawn to establish the flux in it. Means you have an infinite magnetizing reactance as well as core loss resistance like. Now, what are the two components of no load current in the transformer? The answer is the magnetizing current, that is we call it reactive or wattless current, it is magnetizing the core, and second component is the IW, that we call it core loss or active, or what full current is supply the hysteresis and eddy current losses, and negligible I square losses, because no load current is quite small in transformer, order of 1 to 5% like of the rated current. How much is the no load current of the transformer? No load current of the transformer is varying normally 2% to or 3% to 5% of the rated current of the transformer. What is the silica gel used in the breather? The silica gel is used to absorb the moisture when the air is drawn from the atmosphere into the transformer. What is the color of silica gel in dry stage when saturated with the moisture in a breather? So, dry stage it is a deep blue, and under saturated stage it is whitish pink. What is the Buchholz relay? It protects the transformer from the internal faults like earth fault, winding short circuit between the phases, and puncture of the bushing, etc. Give equivalence resistance, reactance and impedance referred to primary. So, R equal to R1 plus R2 dash, that is R1 plus A square R2 dash, and X equal to X1 plus X2 dash, that is X1 plus A square X2 dash, and Z equivalent is Z1 plus Z2 dash, that is Z1 plus A square Z2 dash Z2, and where A is T1 upon T2. So, list some methods of cooling of transformer. I mean, transformer are cooled like cooled air blast, oil natural, air force, oil natural, water cooled oil force, oil force air natural, oil force air natural, and oil force water force at. How much is the leakage reactance of the transformer? In the transformer, the leakage reactance is reduced by interleaving the high voltage and low voltage winding. Now, coming to some of the solved numerical problems. So, starting from first problem, a single phase transformer has a 1000 ton on the primary and 200 tons on the secondary. The no load current is drawn 3 ampere at a power factor of 0.2 lagging. Calculate the total primary current and power factor at primary when the second is loaded to a current of 280 ampere at a power factor of 0.8 lagging. Assume the voltage drop in winding to be negligible. So, now coming with according to Phasor diagram. So, I2 dash equal to I2 into N, that is I2 into N2 upon N1. So, I2 dash into 1000 equal to 282 into 200. So, I2 dash will be 56 ampere. Secondary side is a typically like a is transferred to 280 ampere, comes as a 56 ampere on the primary side, and cos phi 2 equal to 0.8 and cos phi 0 is 0.2. So, I1 cos phi 1 is equal to I2 cos phi 2 plus I0 cos phi 0, that is the loss active component. So, it is 56 into 0.8 plus 3 into 0.2, that becomes 45.4, and I1 into psi 1 equal to I2 dash sin phi 2 plus I0 sin phi 0. So, putting the value 56 into 0.6 and 3 into plus 3 into 0.98, it becomes 36.56. So, I1 is typically now 58.3, because you got the both component of I1, and tan phi is 36.54 divided by 45, that becomes 0.805, and phi 1 is 38.80 degree. So, primary power factor cos phi 0, that is 0.78 lagging. Now, coming to second numerical problem, a current transformer has a single turn on the primary winding and secondary winding of 60 turns, and the secondary winding is connected to the ammeter with the resistance of 0.15 ohm, and the resistance of secondary winding of is 0.25 ohm. If the primary if the current in the primary winding is 300 ampere, determine the reading of the ammeter, the potential difference across the ammeter, and then the total load VA in the secondary. So, here N is given 60, so I2 is equal to I1 by N. So, it is a 300 by 60, that is 5 ampere, and V ampere ammeter will be I2 R ammeter, that is 5 into 0.15, that is 0.75 V potential difference across the ammeter, and RT will be R ampere plus RS, that will be 0.15, 0.25, that is 0.4 total resistance across the secondary. So, total resistance, total load on the secondary will be PS I2 square RT, that is 5 square into 0.4, that is 10 VA. Now, coming to the numerical problem third, a voltage transformer has a 4000 turns and primary turns and 220 secondary turns. So, if the voltmeter reads the shows the 110 volt, how much the voltage at the primary winding. So, here the primary winding voltage is your V1 equal to V2 dash by N. So, 110 divided by 20 by 4, typically 4000, that becomes 22 kilovolt like. So, coming to the numerical problem 4, a 2400 volt divided by 400 volt single phase transformer takes at no load current of 0.5 ampere and has a core loss of 400 watt. Determine the value of the magnetizing current and core loss component of the no load current. So, P core loss equal to V 1 I 0 cos phi 0 and cos phi 0 is P core loss of V 1 I 0, that is putting the value 400 2000 divided by 2400 0.4 equal to 0.33, and now core loss component of no load current I O L equal to I 0 cos phi 0, that is 0.5 into 0.33, that is 0.16 ampere. Magnetizing current is I O M equal to I sin phi 0, that is 0.47 ampere. Now, coming to numerical problem 5, a transformer takes a current of 0.8 ampere when the its primary is connected to a 240 volt 50 hertz supply with the secondary being open circuited. If the primary absorbs 72 watt, determine the iron loss current and B the power factor on no load and C the magnetizing current. So, the no load current I 0 equal to 0.8 ampere, core loss is 72 watt. So, P core loss equal to V 1 I 0 cos phi 0. So, cos phi 0 is P core loss upon V 1 I 0, that is 72 divided by 240 into 0.8. So, it becomes 0.375, that is no load power factor, and iron loss component is O L equal to I 0 cos phi 0, that is 0.8 into 0.375, it is equal to 0.3 ampere, and magnetizing current I O M equal to I 0 sin phi 0, that is 0.74 ampere. Now, coming to the numerical problem 6, a single phase transformer has 480 turns on the primary and 90 turns on the secondary. The mean length of the flux path in the core is 1.8 meter and the joints are equivalent to an air gap of 0.1 millimeter, and the value of the magnetic field strength in the core is 400 ampere per meter for a flux density of 1.1 Tesla, and the corresponding core loss is 1.7 watt per kg at 50 hertz. The density of the core material is 7800 kg per meter square. If maximum flux density achieves 1.1 Tesla when the potential difference is 2200 volt RMS at 50 hertz is applied to primary, calculate the cross sectional area of core, secondary voltage at the no load and the primary current and power factor at no load. So, coming to here, N 1 equal to 480, E 1 equal to 2200 volt, F equal to 50, B m equal to 1.1 Tesla. Using a EMF equation of transformer, so E 1 equal to 4.44 F phi m N 1. So, phi m comes here putting a value 2200 divided by 4.44 into 50 into 480, that comes 0.0206 Weber, that is a peak value of flux in the core. And now, core cross section area we can find out equal to phi m upon B m. So, that is 0.0206 divided by 1.1 and that becomes 0.0187 meter square. So, now coming to typically for the P part, N 2 equal to 90, N 1 is 480. So, V 1 is 2200 volt. So, no load secondary voltage is V 2 equal to N V 1, that is 90 by 480 into 2200, that is 412.5 volt, and B m equal to 1.1 Tesla, HMC is 400 watt 400 ampere per turns in the core, and IC equal to 1.8 meter length of core, and LA is 10 to power minus 4 meter, that is length of air gap. So, MF required for the core is HMC, LC, that is MF into 400 into 1.8, that is 720 ampere, and MF for air gap is HMA into LA, that is BM upon mu 0 into LA. So, MF for air gap is 1.1 divided by 4 pi into 10 to power minus 7 into 0.001, that is 87.53 ampere. So, therefore, total MF applied to produce the given flux is MF T equal to MF core plus MF air gap, that is 720 plus 87.53, that is 807.53 ampere. So, the applied MF is total is N 1 into IOM. So, where IOM is the magnetizing current. So, IOM is MF upon N 1, that is therefore, the peak magnetizing current is your IOM equal to 807 by 0.3 divided by 480, 1.68 ampere, and RMS value of magnetizing current will be IOM equal to IOM peak divided by root 2, that is 1.19 ampere, and volume of the core is that is 0.0187 into 1.8, that is 0.0336 meter square. So, mass of the core is volume into density, that is 0.0366 into 7800, this becomes 262.55 kg, and core loss is 1.7 watt per kg. So, total core loss will be your P core equal to 262.55 into 1.7, that is 446.3 watt. So, now P core loss equal to V 1 IOL, where V 1 IOL are the RMS quantity. So, IOL will be P core upon V 1, that is 446.3 divided by 2200, that is 0.203 ampere, that is core loss component of load node current, and total node current of the primary side will be I 0 under root IOL square plus IOM square. So, that is under root 0.203 square plus 1.19 square, that is 1.207 ampere, and no load power factor is IOL upon I 0, that is 0.202 divided by 1.207, that is 0.168. Now, coming to numerical problem 7, a single phase transformer have a turns ratio of 1 to 2 and the connected to purely resistive load as shown in figure. The magnetizing current is 1 ampere and the secondary current is 1 ampere. If the core loss and leakage reactance are negative, find the primary current, it is shown here. So, you can say secondary current is I 2 at 1 at the angle of 0. So, secondary referred to primary will be I 2 dash equal to N 2 upon N 1 into I 2, that is 2 upon 1 into 1 at the angle 0. So, it is a 2 at the angle of 0 degree ampere, and at the core loss is neglected, magnetizing current will be phase shifted with the flux. So, therefore, I m is induced EMF by 90. So, I m is 1 ampere at the angle of 90 degree. So, primary current will be I 1 equal to I m plus I 2 dash, that is at 1 ampere at the minus 90 degree angle plus 2 at the angle of 0 degree. So, it becomes 2.24 at the angle of minus 26.56 ampere. Now, there are some unsolved problem typically, which you can solve on the similar line, and these are the references or books from which this material is developed of this lecture, and thank you.